Hello everyone! This video introduces the concepts behind the GEGELATI framework. GEGELATI, which stands for Generic Evolvable Graphs for Efficient Learning of Artificial Tangled Intelligence, is a reinforcement learning library developed by the Vaader research team from the Institute of Electronics and Telecommunications of Rennes in France. I am Carol Desnos, and I will be your guide for this video. Reinforcement learning is one of the many branches of machine learning techniques. In reinforcement learning, an artificial intelligence is placed in a playground and must learn to do something useful all by itself. But how does the magic happen? To teach itself something useful, the artificial intelligence, which is called the learning agent, must interact with a digital playground called the learning environment. The learning agent has the ability to observe the current state of its environment and can interact with it through a set of actions. As a result of these actions, or because of external phenomena such as time or physics, the state of the learning environment may change. By observing the constantly evolving state of the environment, the learning agent has the possibility to react and to build a meaningful sequence of actions. For the learning agent to learn which sequence of actions are useful and which are not, an additional reward mechanism is needed between the learning environment and the agent. After playing with the environment for a bit of time, this reward mechanism will tell the learning agent whether its actions were good or bad, helping it to select the most rewarding behavior. Let's have a look at a more concrete example of a video game learning environment. In this example, the learning agent will receive the array of pixels of the screen as the observable state of the learning environment. The learning agent actions on the environment consist of pressing the controller buttons to control the game. Finally, the reward in this context will be the score of the game after playing for some time or after reaching a game over. In this learning environment, like any player would, the learning agent plays the game again and again until it finds the best strategy possible to maximize its score. Now, let's focus on the brain of this learning process and the mechanisms powering it. Many different machine learning techniques are available to power the learning agent, like deep learning, Q-learning, tangled program graphs, and many others. The learning algorithm used in the GEGELATI library is called a tangled program graph, or TPG for short. TPGs were first introduced in 2017 by Stephen Kelly and Malcolm Haywood from the Dalhousie University of Halifax in Canada. As indicated by its name, the learning algorithm behind TPGs is modeled as a directed graph. In a graph, three types of elements can be identified: teams, which are the internal vertices of the graph; actions, which are the leaf vertices of the graph; and programs, which are the edges of the graph. To understand how a TPG works, we must first understand what we call a program in this context. From afar, a program can be seen as a black box that takes a state of the environment as its input, processes it, and produces a number as an output. On the inside, a program is a list of instructions like addition, multiplications, or more complex functions like the exponential function. Arguments of these instructions can be selected pixels of the environment or the result of a previous instruction. Finally, the result of the last instruction is the result of the program. In the video game example, action vertices are each associated to a combination of buttons to press. The best way to understand how a TPG works is to see step by step how it reacts to each new state of the learning environment. When a new array of pixels of the screen arrives, the execution of the TPG starts from the root vertex of the graph. Starting from this root team, all programs associated to outgoing edges are executed on the pixels of the environment. Once all program results have been computed, the largest return value is identified. Following the path given by this value, the execution of the graph continues. Eventually, the TPG execution will reach a leaf vertex of the graph associated to an action. This action is executed, and the TPG restarts its execution on the next state of the environment. In order to build a TPG graph capable of setting new high scores in your favorite video game, a genetic learning algorithm is used. The basic principle of genetic learning algorithms is to simulate an evolutionary process of an artificial intelligence over multiple generations. Generation after generation, the evolution process ensures that the AI improves its performance within a learning environment. Let's see how this evolutionary process applies to tangled program graphs. During the learning process, instead of a single root team, the TPG graph possesses several ones. Each root vertex represents a different starting point for executing the graph, each leading to a potentially completely different behavior of the AI. During each generation, the performance of the AI starting from each of these roots is evaluated separately within the learning environment. To create the graph for the next generation, the root vertices with the worst performance are identified and deleted from the graph. Then, new root vertices are created for the new generation by copying randomly selected teams and their outgoing edges. The new roots then undergo a random mutation process altering some of their outgoing edges, thus creating a new original behavior. As a result of this mutation process, some roots of the previous generation may become an internal node of the graph. At this point, two natural questions to ask ourselves are: how efficient is this genetic learning process? And how do tangled program graphs compare to other modern artificial intelligence techniques? To answer these questions, the performance of TPGs have been evaluated within the arcade learning environment. The arcade learning environment is a framework for training artificial intelligences to play old video games. To do so, it offers a collection of 50 Atari video games like Pac-Man, Space Invader, or Breakout. The main strengths of tangled program graphs observed in this environment are 1. The efficiency of its training, which automatically adapts the TPG complexity to each game and reaches superhuman high scores. 2. The rapidity of its computation, which requires only a few microseconds to process each frame of the game on a common desktop computer. And 3. The simplicity of its model, which requires at most 100 kilobytes of storage for the trained graph and its programs. These results are even more impressive when compared to their main competitors, which, for comparable scores, exhibit both a much higher computational complexity, a much slower speed of execution, and often require hundreds of megabytes of storage for their models. All of this brings us back to GEGELATI. GEGELATI is a framework for easily training and executing tangled program graphs in your own learning environment. GEGELATI was created by the Vaader public research team and is distributed as a C++ library. In order to make integration with your code as simple as possible, GEGELATI is portable and released under an open source license. The code of the library is fully documented, and continuous integration is used to ensure the quality of our code meets strict quality standards. In addition to the basic mechanics of tangled program graphs, GEGELATI already supports additional original features such as training and execution on multi-core CPUs, custom instructions for building the programs of your graphs, and a dot exporter for visualizing the results of the learning process. To start training GEGELATI in your own learning environment, all you need is to create a C++ class with 7 basic methods. 3 methods to create your environment and give it state to the learning agent. 2 methods to allow the learning agent to control the environment, and 1 last method to give rewards to the learning agent. And that's all. So, if you are eager to start playing with GEGELATI, simply go to our GitHub page. On GitHub, you'll find all the resources you need to try GEGELATI on our open source applications, but also everything you need to build your own learning environment. Thanks for watching, and make sure to add our project on your watchlist on GitHub to be notified of future releases of GEGELATI with tons of cool new features.